Practice question set number 7. It starts off with this page of information to answer one question, which happens to us a lot. Last semester, I think the diploma exam was 35 pages for 50 questions. So we get a lot of reading for, oftentimes for just one or two questions. Okay, this one talks about a Van de Graaff generator. It says an experiment is performed using an initially neutral metal sphere in the positively charged dome of the Van de Graaff generator. I'm going to underline that actually, because usually in a Van de Graaff generator, certainly yesterday when we did our little activity, we're used to seeing a negatively charged dome of a Van de Graaff generator. So we notice that it's positive. Okay, that might not make a difference, but I'm going to just underline that just in case, just because it's not what I'm used to seeing. The metal sphere, which hangs on a thread, touches the dome of the generator and is then repelled. We did essentially that exact thing yesterday. We didn't measure the mass of the piece of metal, the pop can, as it was for us that we touched to it. So we got a couple observations here. Yeah, he says, diagram below illustrates the metal sphere in equilibrium. What does equilibrium mean? What does equilibrium mean? Yeah? Not neutral, no. Balance? Good. Yeah, in any context, pretty much equilibrium means balance. In the context of physics, equilibrium will mean balanced forces, yeah. So that means that this metal sphere has, well, who knows what force is acting on it, but whatever forces they are that are acting on it are going to be balanced. Has to be, right? If it's not moving, then it can't have an unbalanced force, otherwise it would start moving. And then what do we got over here? This other diagram shows, looks like a vector diagram. It's not really a vector diagram. It's more of a free body diagram, I guess. Yeah, a vector diagram would have a resultant vector drawn like this. Yeah, actually there is no resultant vector because all three of them add up to give me 0. And you can see that here. We have a force of gravity acting down on the metal sphere. A force of gravity acting down on the metal sphere. We have an electric force acting this way on the metal sphere. We know that because it's pushed away from the dome of the Van de Graaff generator. And then we have a force of tension acting this way. That's usually the way I draw a free body diagram. They have them drawn like this. Doesn't really matter. In the end, it's the same three forces. Okay, so what are they asking me here? What are they asking me? When it touches the generator, the metal sphere becomes what? Positive or negative? Becomes what? Good. Now, is this metal sphere going to balance out with the dome of the Van de Graaff generator? It wants to, right? Is it going to balance out perfectly? Probably not, right? Probably not, because the sphere is likely going to be smaller than the dome of the Van de Graaff generator, so it's probably not going to hold as much charge. But even if it doesn't balance, okay, one was 0 and one was plus 10. They want to become plus 5 and plus 5. Well, it's probably going to be more like 1 and 9. But the law of conservation of charge still says they're both going to become positive, not necessarily equal positive. Does that make sense? So it does become positive. The answer is either going to be C or D, and that's as a result of the transfer of. Yeah. Okay, want to say protons? It would be electrons. Yeah, it's a transfer of the electrons because the protons aren't going to transfer anywhere, right? If you have something that's neutral and you have something that's positive, it doesn't mean in order for this to become positive that positives have to go this way. What it means in order for this first small metal sphere to become positive is that electrons go this way. Okay? That makes this one less positive and it makes this one more positive. Does that make sense? It's always electrons that are being transferred. Always. No matter what the context of the question, if something's being transferred, context of electricity, it's going to be electrons, not protons. Even when in a case like that, it looks like it should be protons. Yep? Well, they want to balance out. Like if this one is, let's say, plus 10, and this one is 0 or neutral, they want to balance out to be +5 and +5. But the reality is, in this situation, they probably wouldn't balance out because one is smaller than the other. If they're equal size, equal shape, same material, and so on, yeah, they're going to balance out when they touch. These guys probably aren't going to balance out. But in the end, it doesn't really matter if they balance out because we know they're going to attempt to balance. And in that attempt, the total charge is going to remain 10. And whether it ends up being 1 and 9 afterwards, or 2 and 8, or 5 and 5, doesn't really matter. They're both positive. Okay? So all that information to answer that. Next one says, 3 identical conducting spheres, 1, 2, and 3, have initial charges +4, -2, and -4. See the symbol there for charge, Q, right? Lowercase q. What does this UC thing mean? That's microcoulombs, and you're not sure what that prefix is, micro. Check your data sheet. On your data sheet, it's in the middle of your data sheet. It'll say a microcoulomb is 10 to the -6 coulombs. I'm going to circle these 3 because they're non-standard units. And we know if we do a calculation, a significant calculation, we have to be in coulombs. Pairs of spheres are brought into brief contact without grounding, whatever that means. We'll see that today. And then separated in the following order. So 1 touches 2, then they're separated. 2 touches 3, then they're separated. And then 1 touches 3, then they're separated. What's the final charge on sphere 1? This is like we did, I believe it was example 3 yesterday. We have charge 1, 2, and 3. We start off as +4 microcoulombs, -2 microcoulombs, and -4 microcoulombs. When 1 touches 2, what are they going to balance out to be? 4 plus -2 is 2. Divided by 2 is 1. So they're going to balance out to be 1 and 1, and this one stays -4. Then 2 touches 3. 1 and -4 becomes -3. Divided by 2 is -1.5. So we're going to say now we got -1.5 right here, -1.5, and then this one remains 1. And then we see that 1 touches 3. So we got 1 and -1.5. That's going to be -0.5 divided by 2, -0.25. And of course, these are all times 10 to the -6 coulombs or microcoulombs, right? So what's the final charge on sphere 1? Looks like -0.25 microcoulombs. My answer is C for that one. Good? How many people got that one? Good. Good. And this is the last one, I think, isn't it? It says the number of excess electrons on a ball that has this amount of charge, expressed in scientific notation, is what? We're not asked for the number of electrons that this ball has. Okay, we have no idea how many electrons it has. Okay, we know that the extra electrons, the number of electrons beyond the number of protons, gives us a charge of -3.6. How do we find the number of them? How do we find the number of anything in physics? It's always going to be a total divided by the amount for 1, right? I wrote that on the board yesterday afternoon. The number is the total of something divided by the amount for 1. So in this case, it would be the total, what variable do we use? Charge divided by the charge of 1. Electrons. So we're going to say -3.60 times 10 to the -17 coulombs divided by -1.60 times 10 to the -19 coulombs. And I believe that was 225, isn't it? 225 electrons. In scientific notation, that would be 2.25 times 10 to the 2, and we would express our answer there, 2252. How many people got that one?